So the three problems that I solved in this lab were first getting a Roomba to clean one spot in a map that looks something like this, then having it find an optimal way to clean multiple spots in a map, and then making some slide puzzle solution, which I'll show later. So the way that I did all of these was using different search algorithms. I would search a bunch of different paths to solutions to goal states. Some of these that I implemented were random search, and I used tree search and base tree search, graph search, and uh, an anytime search algorithm. And using these algorithms, I ran them with the depth for search, breadth for search, uniform cost search, greedy best search, and A-star search. And I made these applicable for all three of these types of problems. So the first problem that I solved using was trying to get the Roomba to basically clean up the dirty spots, which are represented by the red tiles. It can't turn over, it can't go through the walls, which are the gray tiles. The green tiles cost 1 to go through, and the blue tiles cost 2 to go through. So the the first thing that I made was random search, which basically just picks a random thing every time, and it's not very good. It'll waste a lot of time exploring things it's already explored. In this section, it shows the number of extents and queues that were used to find the solution, and there's other information that gets produced while the algorithm is running here. So the next thing I made was DFS, and this takes a lot less time than random search. But it's also somewhat flawed. It doesn't always find the optimal solution. I also made BFS, which basically checks and it finds the shortest path, which is going through these blue tiles. But this isn't actually the most efficient solution because there's better solutions that go through the green tiles that cost less. The next algorithm I implemented was UCS, Uniform Cost Search. And this one, I think, does actually find the optimal solution in this case, or one of them. And but it does take some time. It explores a lot of unimportant or useless states before finding the solution, which is the best one, but it does take some time. The next thing that I implemented was greedy search, and this requires some heuristics to be used. Like in this case, I used Manhattan distance, which is just the number of tiles that is away from the goal. And when I run it with this, it'll basically instantly find the shortest distance to the goal state. In this case, it's using very little time. It's only 11 extents and 14 NQs, but it doesn't find the optimal solution. It does cost more. The last one that I implemented was A-star search. This one I also need to give it the Manhattan heuristic, and it this time it should find the optimal solution, but it does take a bit more time than the greedy search. The other core algorithms basically are slight variations to this tree search. What graph search does is it ensures that it'll never look at the same state twice, or it'll never be at the same, basically it'll never search the same point multiple times. So if right now it's 38 and 50, but if I run a star again using graph search, it comes in at 25 and 27, which is pretty helpful. It saves a lot more on the other algorithms like UCS, BFS, and DFS. The anytime search is basically the same thing as graph search, but the main difference is that it'll find out which, it'll basically return whichever state it thought was the closest to the goal. So if I terminate it early or it ends, or like it uses all of its length or cost cutoff, it'll just return, let's say, this state which it thought was the closest to the goal. It was only 2 tiles away. So that was my first part of the lab. Then I went on to doing multiple dirty tiles. And this one, there isn't too much that's different with any random DFS, BFS, or UCS. The only things that really changed a bit are greedy and A star because I'm using different heuristics. So the heuristics that I used in this one are total Manhattan, which is like find it'll find the closest state, it'll find the closest dirty spot, and then it'll find the one closest to that and closest to that, and so on. But it'll use the Manhattan distance, so it won't give a perfect solution. The other heuristic that I used was closest Manhattan and spots left. So what that will do is find the number. It'll find whichever tile it thinks is the closest, and then it'll count the number of spots remaining and multiply it by 3 and add it. So it'll like prioritize it being 3. However, because while usually this works pretty well, this isn't technically admissible because, for example, if there were multiple states next to each other, it would end up overestimating what the actual cost would be. So running this is a total Manhattan thing, which in general works pretty well. This case it's 30 XNs and 40 NQs for greedy, and then the closest Manhattan and spots left just it does waste time because it does waste some time in greedy search, I think, before finally wait. Oh, I think okay. Okay, so the other problem that I solved was a slide puzzle in GUI, and this one or was a slide puzzle problem. So here there's a bunch of different files, but let's do, I think this one. Yeah, okay, so basically the goal is to get the tiles like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. Leave, it'll put everything in order and have an empty space here. So this problem is actually really easy. It's just moving the 10 and the 9. And this is mainly, the best algorithms here are greedy and A star because a lot of times random just, if it would take a really long time for random to find any solution at all, and when it does, it would be a very inefficient one. So the heuristics that I made here are Hamming and Manhattan. So what Hamming is it's basically the number of tiles that are out of place or in the wrong spot. In this case, it would be 2 because both the 9 and the 10 are in the wrong spot. And the other heuristic that I made is Manhattan. So what that does is it finds the number of tiles that are in the wrong spot, and then it looks at each tile and finds the distance that it is from the closest, I mean from where it's actually supposed to be in the solution. So in this case it is also 2, but if I shift it around a bit, it'll give a different evaluation than the Hamming because they're farther away from where they're actually supposed to be. So if I run it, greedy will find the best solution basically instantly as compared to random, which is really slow. And so should A star. But if we run it on something a bit more complex, um, So if we go to a, let's say, 4x4 solution, 4x4 problem, this one, if greedy, if I run it, I'm going to do graph search so it's a bit faster, and I need to give it. So greedy takes some time to run. Um, okay, basically this is an example of why greedy isn't always the best solution, because it's exploring using depth and it's not actually considering all of the possible solutions. So even when it does finally return a solution, it would be a very long cost, or it would be a very large cost. I think in this case, A star should perform a lot better. Okay, so it did work, but and I'm pretty sure I found the one of the optimal solutions. I think the solution here was supposed to be 12 tiles deep, but I'm not 100% sure. So it did explore a lot, but it did find one of the solutions basically, um, for a pretty complex problem.